Okay, so this section 8.2, derivatives of exponential functions. If you're wondering what exponential functions and logarithmic functions are all about, you can look at some other videos on logs and exponential functions, including the video we just got finished in this class here, involving some of this stuff right here. But 8.2 is all about a special base for an exponential function. But let me set this up real quickly. When we're talking about modeling, something that is growing exponentially. All right. So what I'm talking about is, let's say we're talking about the exponential growth of a population over time. All right. And okay, something like this. It's always rolling around. So when we're talking about exponential growth of a population of people or of bacteria or anything like that, we would basically draw some generic exponential graph, right? Some exponential curve. And I'm just going to fix this a little bit so it doesn't look like it's dipping down. But we would draw something like this, and we would say it's growing exponentially. Now, what would we actually choose for a base? Would you choose 2 to the power of x? Would you choose 5 to the power of x? And you say, well, Mr. Maxwell, it depends on how fast the growth is. Well, that's true. That's true. I mean, you could have different, slightly different growth patterns, and that is important. That's very, very good. But if we're talking about a generic sort of exponential growth, and we can vary, like really, we could vary the scale here. We just want some nice exponential shaped graph. In calculus, it would be nice to know if there's a certain base that is, how can I say this, calculus friendly. So there are some functions that are really easy to take the derivative of, right? Like even in our basic differentiation. Okay, so like, y equals x squared, plus 2x minus 5, okay? That graph is very, very close to y equals x squared. It's a little bit different shape, but it's pretty close. Which one is easier to take the derivative of? Well, they're both easy, right? I know they're both easy, but this one would be simpler. It would take us less time to find the derivative, even though they're both easy. Now, you may or may not be agreeing with me or following, but what I'm saying is that in calculus, there does exist a special base that makes calculus calculations easy, or specifically makes finding the derivative. So there's a base that makes finding the derivative of that function really, really easy, and I just want to kind of explain to you how we arrive at that base. Okay? Okay. All right. So we're going to take two exponential functions, y equals 2 to the power of x. Well, actually, I'm going to put that over here. Y equals 2 to the power of x, and y equals 3 to the power of x. Now, let's just make sure, and just turn this calculator on here. So I've got y to the 2 to the power of x, about 3 to the power of x. Let's graph those two. So 2 to the power of x is going to get graphed first, and then 3 to the power of x is going to get graphed second, and here it is. So that's a bit steeper, right? Okay? Both sort of exponential growth graphs. All right, if you look in your book, and I don't think I'm going to take the time to make you do this, but if we look at, let's see, 0.1, 8.2 is what I want. Good. So I'll look at this already. So 8.2. You guys remember this? This right here? This is the definition of a what? This is the definition of a... Oh my... Really? No one? No one? Sadness. Sadness is overwhelming me. I'm even sadder about that than the fact that SJ is sleeping back there. Hey, wake up. Oh boy. Wipe the drool off your cheek. This is the directly finding the... What is this, guys? Do you remember finding the derivative directly from the definition of the derivative? Remember that? Chapter 1-ish, 2-ish, 2.1? Yeah, it's blurry. Yeah? That was back when calculus was easy, remember? I thought calculus was hard back then for you guys, no? You said this was hard. Okay, but now, comparably, it's easy? Okay. So anyways, so what happens, look at what happens if you evaluate the derivative. Now this is just an expression for the derivative of some random exponential function with a base b, okay? You have to follow along very carefully here. So we're going to put b to the power of x plus h minus b to the x all over h. So what you can do here is you can actually use the laws of exponents to separate b to the power of x plus h into the b to the x times b to the h, right? When you do that, do you see that you have a common factor of b to the x? That can be removed, and because it doesn't have anything to do with h, it can be pulled out to the front, basically as a constant. All right? Now, if you didn't get that, that was too fast, then, well, you can write it down. It's in your textbook if you want. Yeah, I mean, you can write this down. But what we're going to focus on is this part here, the limit part. Okay, that's what we're going to focus on right now. Okay, so if we look at this a little bit closer, what you're going to notice is that the derivative of b to the x can be expressed as some limit times b to the x. Look at this, times the original function. So just looking at this same thing right here, see? The derivative of b to the x, right? Look at this, is b to the power of x. We're taking the derivative of this, and it actually can be expressed as its own self times the value of this limit right here. How is f prime of x b of x? Well, that's what we just went over this right here. Okay? I'm taking the derivative of b to the x from the definition of a derivative from this. As we work this through, do you see how there's a common factor b to the x here on top? Pull that out. See? How did b of x come up? We're taking the derivative of this function, b to the x. So this f of x plus h becomes b to the x plus h, because that's the function we're dealing with here. Okay? So the original function is b to the x, just some base. So I'm getting an expression now for the derivative of an exponential function with really any base. Okay? But what I'm saying is that the derivative can be written as the original function times this limit, some value of some limit. Okay? Now what's interesting about this is that these two exponential graphs that we've just looked at, if you evaluate 2 as a base and 3 as a base, this is the chart that you get. Alright? So again, we're trying to find this limit. There's no real fancy algebraic way of just throwing 0 in there or factoring h out. Can't do it. But if we evaluate the limit and sort of look at what is happening here, for y equals 2 to the power of x, that's what this is, right? If we let h approach 0 for this function, the limit here becomes about 0.69. You see that? It's approaching about 0.69. So that's kind of what our limit is for 2 to the power of x. If we try and find an expression for the derivative of y equals 3 to the power of x, so that's, we plug that base in there, and we let h get really, really small, this seems to approach what value? Pretty close to 1, right? Maybe 1.090 maybe. So right now this doesn't look all that shocking, but consider this, and this is the most important part of this whole lesson. If this right here, if this limit was to equal 1, then we would have the function is b to the x, and its derivative would be b to the x times 1. So do you see how if we found a base where this limit actually equals 1, then the derivative of that particular exponential function would be itself. It would be itself times 1. So once again, the limit of y is equals 2 to the power of x is approaching somewhere around 0.69. And the limit here, when 3 is the base, is about 1.09. So somewhere in between 2 and 3, do you see how the limit with that special base should be 1.000? Somewhere in there? Does it make sense? Because this is 0.69, this is 1.09. So somewhere in here, there should be a base, y equals something to the power of x, where this part of the definition of the derivative, where this part right here, I'll just highlight for you, where this part, I like the highlighter, should equal 1. And there is a base that we can identify, and that is a special number called, well, it's labeled e, lowercase e, and you will have that on your calculator, and you should see that in your notebook, your textbook as well. It is approximately equal to, it's an irrational number, but it's approximately equal to 2.71828. And that is the special base that we use in calculus, 2.71828. That's the special base. It's given a special symbol, and that's e. And why is this important? Because if you have e to the power of x, and it's going to look very similar to 2 and like y equals 2 to the power of x, y equals 3 to the power of x. But if you have this as a graph, y equals this, and you want to take the derivative of that exponential function, guess what? The derivative is itself. So the special part of e as an exponential base is that the function e to the power of x is its own derivative. And I'm just going to spend just a couple more minutes explaining what that looks like. So y equals e to the power of x is just going to look like some random exponential function. But here's some cool stuff right here. This is going to be y equals 1. And what this means is that the derivative, the actual value of the derivative at x equals 0 here, the value of the derivative is going to be whatever the function equals at that point. So the slope, or the derivative, equals 1, because that's the y value at that point. Let's say at this point, this was y equals 2 for the function. Guess what the slope is? 2. Isn't that cool? Well, sort of cool. Sort of like teacher cool, not kid cool. At this point, the derivative at where y equals 4 for the function, the slope of the tangent line is 4. Okay, so this is very important. E is a special base because the function e to the x is its own derivative. I'll let that sink in for just a few moments. Okay, e, you guys all find that on your calculator? You should have a little lowercase e, or e to the power of something. Okay, I'm going to adjust this window just a bit here. Alright, on your calculator, here's the E button on my calculator. So I'm going to put second function, this one here, e to the power of x. And you're going to see that it'll graph right in between 2 and 3. Now it's going to be a little bit closer to 3 because 2.7 is quite a bit closer to 3 than it is to 2. But that's where it is, right there. Okay? And so the derivative at this point is, at y equals 1, the derivative is 1. The derivative at y equals 2 here is 2, and so on. Alright, so if we were trying to find the derivative of this right here, guys, watch this. The derivative of y equals e to the power of 2x is what? What is it? What's your guess? Y, 2? Oh, no. Well, think about it. What did we just talk about? It's the same. Except, well, it is the same. Except, is this x right here? Is that just x? It's 2x. So, what have we been doing? What does this look like? Chain rule. Yes. Chain rule. Chain rule. Times 2. Thank you. This is hard because you have to remember things that you learned before. Did you say that? Is that your challenge with this class? Because you have to remember stuff you've learned before today? Oh, we learned that yesterday. Come on. Oh, like in other years. Yeah. You have to put it all together. Oh, I know. They have to put it all together. That is terrible. I'm almost...
You got it right.
All right. Are you ready? Here is the... Oh, yeah. Sure. Of course. Okay, so... Okay, let me finish my thought here. If you have some function that is not just x, and you're differentiating this function with respect to x, this is where you have to do the chain rule. So it's e to the u times du dx. Or, another way to put it, the derivative of e to the u is e to the u times u prime. Okay? Same food, different bowl. Right? Got it? Chain rule. Now, because you're all excited about, you know, the trigonometric functions. Yes. Okay. Find dy dx. This is easy, guys. No, it's easy for you too. Trust me. Yes. Okay. Yeah, this one's easy. Okay. Boy, I wish you guys whined a little bit more. That would make my life a lot easier. Okay, what do I write here? Tell me. I'm not. Thank you for not changing sine x up here. Thank you for not doing that. Thank you. Times. Wow. Times cos x. Oh, you can run, but you cannot hide. There you go. Work on that for tonight. There will be a lot more where that came from tomorrow. Have fun.